welcome back to our little unit on Lopez rule. First, we're going to start off with another non-indeterminate, or determinate form, which is 1 over infinity. So you think that 1 divided by infinity would evaluate to a problem, but in reality, the limits of this, as x approaches a, 1 over infinity, is just going to equal to 0. Like, if you divide 1 by an infinitely small number, you're just going to get closer and closer to 0 until you have nothing else to lose. So that's not actually a problem, even though 1 and infinity. So let's get into the real problem. So limit as x approaches 6. When we have x squared minus 3x plus 18, x squared minus 3x minus 18, all over x minus 6. What is the limit? Evaluate the limit of this function using Lopez rule if needed. And I'm going to use Lopez rule at least just to demonstrate it. The thing is, this is incredibly easy. If we look at the numerator, and we think about where it's going, we can plug in, we can actually factor something that there's an x plus. X6 plus 3, x minus 6, x plus 3. We can see that if we plug 6 into here, it's going to approach 0, which means that if we, at the limit of that one is approaching 0, as we get closer and closer to 6, which means 0. Same for this one. Plug in 6 for x, 6 minus 6, give me 0. So it is 0. And now this is where the indeterminate form pops out. These are the limits of each of the top and bottom. So we come over here and apply Lopez rule. The derivative, so what we're going to do is we're going to take the derivative of the bottom. So x over the top is going to be 2x minus 3 over g of x is going to be just 1. That's what the derivative of 1 is going to be. And now we can plug in 6 for x, because this is going to be x, which is 6, which is going to be 2x minus 3 over 1. So 6 2 times 6 is going to be 12 minus 3 equals 9, and that is going to be the limit. Simple as that. So let's move on to the result. But for that, I just hope this will make sense. And to reiterate, Lopez rule is just a way to evaluate these indeterminate forms that otherwise are very difficult to evaluate. So let's continue on. Cool. A lot of these are calculus. So let's look at arctan 4x and over ln x. So the limit approaches 0 from the right side, because that's the x approaches 0. We have arctan x of 4x. Arctan 4x over ln x. So as tangent can be changed into whatever tangent of 4x, which can in turn be changed into 1 over sine 4x, cosine 4x, which can in turn be changed to cosine 1 over x. It's going to be, I'm not sure if this is possible. Let me double check this. Okay, I was actually wrong about that. Cosine, or inverse tangent or arctan cannot be turned into cosine, or arc cosine, or or arcsine in any meaningful way for now, but it is sufficient to say that tangent, or arctangent, is going to approach 0 as it approaches 0. So as x approaches 0, tangent of x is going to approach 0. So that means that on top we have a limit that approaches 0, and on the bottom, ln x, it has the parent function that looks like this, where it can get infinitely small, but it cannot be negative, which means that it is also going to approach 0, which means we have an increase. So what we'll do is take the inverse, or derivative of each of these. So the derivative of tangent is going to be 1 over 1 plus x squared. Check that. I do not think I need to, but I will have those. It's kind of hard to just like pull them off the top of your head. But I was correct. And then cotangent is -1. And cosecant is -1. And everything is fine and dandy, and there are no problems. Okay, so back to what we were talking about. Let's get into actually, okay. Alright, so we ended up with this. This is 1 over 1 plus x squared, which is 4x, actually. So 4x squared. Times 4, because we're going to take the derivative together, so it's 1 over 4. And then that's going to be all over 1 over x. So now what do we get? We get, technically x is going to be top of x times 4 over 1 plus 4x squared all over 1. But x is 0, so it's going to be 0 times whatever that was equal to 1, which means we're going to approach 0. So that limit just approaches 0. Easy. Let's make it a bit harder. Yeah, quite so. I thought I would have more time, but it did confuse me. Okay. Oh yeah, this one's a bit more interesting. So limits as x approaches might not be what it is, but limit as x approaches infinity, we have x to the 4th times e to the power negative x, e to the power negative x cubed. Yes. Okay. So, what do we got? We can actually think about these as two separate functions. F of x and g of x. So f of x is x to the 4th, and g of x is e to the power negative x cubed. So, we have x to the 4th times e to the negative x cubed. So for this one, the first one, as x approaches infinity, this number is going to also approach infinity. So the limit is going to be infinity times, what is the second one going to be? So, in this case, we can't evaluate e to the power of negative x cubed by itself. We have to divide. So what we're going to do is we're going to come over here and we're going to have like a miniature problem where we're going to also be applying the multiples rules to figure out what this actually relates to. So as e, actually might be able to evaluate by itself. E to the power of negative x is essentially going to be 1 over e to the x cubed, which means we're just going to be getting really, really small, really, really fast, which means that this is going to evaporate to 0, because the bottom's going to be 0, which means we have the indeterminate of infinity times 0. So what can we do to convert this back into an indeterminate form? That's a good question. I'm not really sure. Let's think about it. So, the notes, 0 times infinity, what we can do, is we can put an e ln on it. So you already know that if you have e to the power of ln something, the e and the ln cancel out, which means that you can put it wherever you want to manipulate things. You'll end up with one. So let's do this real problem here. ln e to the power of ln x to the fourth e to the negative x. What do we get? Well, we can separate these into ln x to the fourth plus ln e to the negative x cubed. And of course, e all the way down here. Now we can get 4 ln x plus negative x. This is probably always to 0. Let's plug in the calculator so we get yep, it's going to be 1. So this is going to write to 1. And this is going to write to whatever it runs. So we're doing this as x approaches infinity, which means we're going to end up with infinity plus infinity right here. And that's going to be, it's not determined anymore because now we have e to e. No one really cares because I do not know what the next step is. Wackles roll, so we get here, and then what we do? We'll figure it out. Okay, so it turns out I was actually completely wrong about this problem. And this is not how you solve it. The way you solve it is first, e to the negative x has to go to the denominator. I'm going to say this right now in the future. If you ever see an inverse or negative exponent, you automatically should be putting that in your denominator. So we're going to end up with x to the fourth over e to the power of x cubed. So we know that both of these, we just want that both of these are going to go to infinity as x approaches infinity. This is going to be infinity, and this is also infinity. Easy. So we know that our indeterminate is pretty simple right now. But what is actually indeterminate? So what we can do is we can take the derivative and get 4x cubed over 3x. That's still not what we need because it's still an infinity over infinity. And so we can go 12x squared over 3x. Doesn't work, we can go 24x over 3x. Until finally we get down to 24 over 3x. And now, the derivative of that is going to end up with the limit at least. That's pushing infinity, we're still going to push up 24. But, I mean, the derivative of that is going to go with, anyways, it's going to go to infinity. So, what can you infer from this? Means that the limit is 0. As x goes to infinity, x is going to go to 0. But why is this? It's because 3 e to the x, or ex cubed, or e to the power of x, power of 3, is going to grow faster than x to the 4th. This is a way to prevent you from having to do all these locals applications and derivative over and over again. Instead, what you can do is just say, oh my gosh, if this is an exponential, it's going to grow faster than this. Therefore, it is effectively going to become anything over infinity. You can say this is a super infinity because it's growing at a rate so much faster than our normal exponent or cubic that it's going to end up giving us an arbitrary top number compared to whatever's on the bottom. So we're going to end up with 1 over infinity because the gap in them is going to be so big that it's going to be a small number that we end up with that indeterminate, and our limit is going to be 0. So, hope that makes sense. Let's continue. So many different ways to apply this. In practice, it's been a lot. Wait till tomorrow to do it. So what is next? Okay, so here we have L'Hopital's rule. Function. F of x. When x approaches infinity is x to the power of a of x. So we can just look at which one's f and which one's g. Well, as x approaches infinity, it's going to go to infinity. And for this one, as x approaches it's going to go to 0. So boom, we have a problem. We ended up with the indeterminate infinity. How do we fix this? Well, we can just put an e element on it, like we tried to do in last one. We're going to get x over x, which can become e to the power of x ln, that's going to be 8 over x, ln x. So, is this all of this? I do not think so. Because now what we have is, as x approaches infinity, we have 0 times infinity still. Because 8 over x, or 8 over infinity, is going to approach 0, that ln of x is going to approach infinity. So we changed indeterminate forms from being 0 times infinity, or infinity to pi 0, into 0 times infinity. So now we can actually just kind of remove this top part of the equation if I'm not wrong. So 8 over x, all x. Think about this. Okay, I know the quick review. This is going to look really stupid, but what you can do to get 0 times infinity into its correct indeterminate form, because if you have an exponential, it's indeterminate, it's always going to look like this. We're going to do ln x divided by x over 8. So, this technically evaluates to 8 over x ln x, but because it is in this form, we can modify it to look different. So, x divided by 8, as approach infinity is going to be infinity over 8, which is infinity. As x approaches infinity on x, infinity. We are now in an invalid indeterminate form. So now all I have to do is just take the derivative to find what we want. So 1 over x, and 1/8 x is such that this is x is going to turn into 1/8. So 1 over x divided by 8. It's going to be infinity. Or 1/8 infinity. Is this correct? No, it's not correct. I will pause. should have worked. We got into an indeterminate form. So there's infinity over 8. Yeah, that approaches. Now on x, the derivative of that is 1 over x. Oh, what was it end up with? Oh yeah, it's going to be. So we can essentially do 8 times 1 over x, and we're going to get 8 over x. And as x approaches infinity, we can end up approaching 0. That's not right. Yeah, that's incorrect. Where is the problem? Let's pause that. Okay, 15 seconds later, and I have my issue. It's because this turned into this, which turned into this, but this is inside a box. And that box is on top of e. There's that. So all of this is e to the power of the numbers in the box. So e to the power of 0 is going to be 1. That is the answer. So what was my error? It's because I forgot that everything that's at the beginning, when you change it, has to be considered once you're at the end. E to the power of this, we evaluate this, but it has to go back to e. So e to the power of this, which adds to 0, equals 1. So, when evaluating limits, you have to consider that. Okay, I think I mostly got that. So here, let's lay down a few ground rules for how to convert different indeterminates to other indeterminates. When you have an indeterminate form of an exponential, so f of x to the power of g of x, the way that you break this down is g of x ln the natural product plane fx. Next, this will always, okay, maybe not always. Actually, yes, always. I'm just going to go ahead and say it's not going to be one of the two indeterminate forms you want. So what you're going to have to do, odds are it's likely going to be 0 times infinity. I think that's all what my examples come out to be. You're going to end up with that. So what you have to do is, second step, if you have 0 times infinity, where it's g of x times fx, what you do is you divide f of x by the inverse of g of x. What this essentially does is it takes the opposite and puts on the opposite. The inverse, if you divide by the inverse, that's essentially saying that I'm multiplying by that thing. Except this is a fancy way to look at it, where, oh my gosh, now I can actually divide, or have the indeterminate form of 1. So odds are this is going to be infinity over infinity, or 0 over 0, whichever one you like. There was one other instance, I believe. Infinity minus infinity, I don't know what to do with that. Oh yeah, so you have infinity minus infinity, what you do is you're going to have g of x minus f or something. What you're going to do is you're going to factor out x in whatever way you can. So x. And then you're going to end up with something on the inside that you can mess with. Because x is no longer a part of it in a sense. So example of that is so I've laid out the values. I'm going to go through two more examples that are important. E to the limit x is going to be e to the x minus x. Yeah, e to the x minus x. So as x goes to infinity, goes to infinity. So we end up with infinity minus infinity. What we're going to do is we're going to factor x out. So we're going to end up with e to the x over x minus 1. So is this look familiar? So e to the x is going to be infinity, and x is going to be infinity, so we're infinity over infinity. And we're going to disregard this x on the outside. We're going to take the inner, and we're going to mess with that. So we're going to apply L'Hopital's rule to that, and we can get e to the x over 1, which will evaluate to infinity minus 1. So infinity minus 1. And then we can take this and go back. And so you're going to have x, infinity minus 1 is going to be the limit. Now, x is going to infinity, so if x approaches infinity, and this is infinity minus 1, what do you think it is? Well, the truth is, it's not indeterminate, which means that the full limit is just going to become infinity. So, in this example, as x approaches infinity, we also are approaching infinity. And that's how you get out of this thing. You just manipulate, you take the factor out, you manipulate the inside, and then you can do things. Okay, one more example of this one is crucial. Else you will get very mixed up. So what is the definition of E? E is this. 1 plus 1 over n power n. Let's double check that. Yes. Exactly. So this is E. Now, I can replace this with C, and all of a sudden, I can make it e to the power of c. So if you ever see something that is the form of this, where, for example, I have 1 as x approaches, the example has infinity, and it's 1 plus, I don't know, the whole over x to the power of x. I can look at it and be like, oh my gosh, that's the definition of in, and simplify it to e to the 12. So, now that I know that x is going to infinity, and this is all I have, I can just say that the limit of the value is 2 to the power of 12. And that's as simple as it, or as hard as it gets. But if you didn't recognize this, you'd be absolutely and utterly lost. So you have to be able to recognize, hey, I have the definition of E right here. That's what my limit is going to go to. So, if that helps, that's all L'Hopital's rule. Some ground rules for how to confront them, as well as what L'Hopital's rule is. And I hope that was helpful, because it was very helpful for me, at the very least.